This is a recording of a talk given by Bryan Kibble at the NPL on the 16th of March 2016 at a meeting on the history of units sponsored by the History of Physics section of the Institute of Physics and the British Society for the History of Science. The meeting was organised by Jim Grosier and me, Terry Quinn, and this recording was made by Jim Grosier with his handheld tape recorder. Bryan Kibble, as many of you know, invented the Watt balance in 1974, I think it was, Bryan. And the Watt balance has been the key to this. Without the Watt balance, we would not have been able to get so far. So, well done, Bryan.
I thought to reading papers of work which has been done, which present a beautifully logical, clear picture of beginning the work and solving some problems, going through to a result and a conclusion. Lovely, clean. Us in the trade know that things are not really like that. So I thought you might be interested to know what the real story of the Watt balance is. It's quite interesting. Let's begin with this current balance, this venerable old instrument at the NPL. Various countries had current balances, and their purpose in life was to get at the ampere. The current balances go back to before the beginning of the 20th century. And the ampere definition came into being to suit the current balances, not the other way round. Comparatively recently, just post-war, I think. So it served well for many decades, but it had some problems. It consists of coils hung from a balance which are suspended inside these fixed coils. And you weigh the force on the coils when on the ones inside when all the coils are fed with a current of a nominal 1 ampere. And that produces a few miserable grams of force. Kind of difficult to weigh with any great accuracy. Worse than that, unbelievably, there are 50 watts of heat produced in the balance case by the current going through these coils. And this, of course, sets up convection currents. And also, again, unbelievably, these convection currents are stable enough that you can work with the thing for about a couple of hours. And then they go chaotic and unstable, and you pack up for a day and go home and wait for it to cool down again overnight. Perhaps you can make this out. This is a plate put across between the coils and the balance beam to try and alleviate that problem. Well, it did a bit, but not greatly. But there are other problems. In order to calculate what the force should be and realise the two parallel wires definition of that, you just wind the parallel wires up into coils, you understand. To do that, you have to know the position of every single point on every single wire of this complicated coil system, meaning hundreds, if not thousands, of length measurements done to the utmost possible precision. And that is not all, because the wires are straight wires deformed into circles to wind them around. Consequently, they are strained across their cross-section. Strain alters resistance of metals, and so you do not know where the current, it has a varying density across the cross-section of the wires. And this you have to take a guess at. And one or two other things as well. And the net result of this is that the current balance had a 1 sigma error of about 20 parts per million. And that was fine when electrical measurements were not that precise. But by the beginning of the 1970s, people had developed digital voltmeters, which they were selling between countries. And they had a resolution and a stability of a part per million. This could only manage 20 parts per million. Worse than that, every national laboratory worth its salt had a version of this. And they all quite properly thought that theirs was giving exactly the right answer. The result of that was there was an English volt, an American volt, and of course a very divergent French volt, 9 parts per million divergent, I think. So the DVM manufacturers began to get rather cross about all this, and clearly something had to be done. Now, to deviate a little bit, I at that time was also hanging a coil up from a balance, but my coil was in a strong magnetic field of a permanent magnet. And its purpose in life was to determine the gyromagnetic ratio of the protons. That is, the ratio of how far the protons precess the magnetic field, which you measure by NMR technique, in terms of the strength of the field, which we measured with a coil of known width. This was a rectangular coil hung up from a balance, and we weighed the force. So I was busy with that, and the work was not going all that well, but I learned of some precise coils which had been made by a Dr. Briggs in the Australian National Laboratory. And unfortunately, the management of the Australian laboratory had decided that since he was retiring, his work should stop. So I thought, if I can take over his coils, which were a beautiful bit of Australian workmanship, glass with a strip of silver conductor, rectangular section around the edge, and you could measure the width between the faces of the rectangular conductors, I could get on a bit faster. So I wrote and asked, and the Australian laboratory very kindly said, well, yes, you can have them, of course. So they packed up these fragile glass coils and sent them across to me. And Dr. Briggs came with them. He retired, and he fancied 6 months in the old country. Fine. And we set about, and it went pretty well from then on. We weighed the coils and so on. But one day, there was a bit of an accident in that this fragile glass coil, suspended in the jaws of this enormous great permanent magnet, imagine it if you will, suddenly decided to take it upon itself to flip like a galvanometer coil and crash against the pole face of the magnet. The damage wasn't too great, and it was still actually usable, but I said some rude words, and Dr. Briggs was very kind. He said, well, don't get cross with the coil, it's really not its fault. Its energy is just the product of the current in it times the magnetic flux threading it. And all it was doing is trying to minimize its energy by rotating transversely in line with the flux, so the flux threading it was smaller. Well, this kind of sounded very interesting to me, because this theorem, I don't know whether any of you know it, that the energy of a current, circulating current, in a circulating magnetic flux is just the product, and they must link, is just the product of the flux times the current. And it's topological. It doesn't matter where it is, how they thread, what shapes the coil are, it doesn't matter what anything is. The energy is just the energy of linkage. Well, that was fascinating, so I stored it in my head and found it quite interesting, and went on playing and got it. Got a result for the gyromagnetic ratio of the proton. And then this current balance was in trouble, and Dr. Vigro was about to retire, and I could sort of see that this machine would be coming my way to improve by a factor of at least 20, and that I would have to perform all these thousands of measurements and try, and I did not like this idea one bit. So, in desperation, I started to think along the lines of, well, okay, there's a force due to the current and so on, and it depends on the size of the coils. Now, suppose we move one coil inside the other. That will generate a voltage. And voltage will also have something to do with the geometry of the coils, won't it? And this idea went round in my head for a little while, getting not very far, when I suddenly remembered Dr. Briggs and his incredible threading theorem. So I'm reliably told if I press that, I'll get the next slide, but I don't. Let's press that. Ah! Oh!
Too far.
You went to press it once. Right. We get there, experimentalists in the end. There's this theorem, E equals I5, where I is the current in some loop or other, and phi is the total amount of flux threading it. And some elementary little bit of calculus somehow entered my head. Okay, that's a force, that is dE by dx. And so there we are. Let's weigh the thing. I was used to, remember, to weighing coils in fields. mg is the force, is I d phi by dx. Okay. What about the voltage? And this is where...
Do you want this little pointer?
Well,
Press right at the very top.
it's just another thing to go wrong, but yeah. Thanks, Terry. Yes, it would help. And voltage, as we all know, is dψ by dt. And one day, it just suddenly entered my head, dψ by dt. Well, hang on, that's dψ by dx times dx by dt, isn't it? Yeah, okay. And dx by dt is velocity. dψ by dx, where have I heard that before? Oh, there. Oh, what happens if I eliminate it between the two equations? All this took about 2 seconds in 5 meters walk from the library, getting to 6 meters from the library. Hence this. And the Watt balance was born. You can measure I by the volts developed across a resistance R, and then you have an actual usable equation there. But it's voltage and not current. But resistance by this time, the early 70s, the calculable capacitor had been invented and so on, resistance was in good shape. So you could get current voltage by Ohm's law. So there was no problem. So here we have a replacement for the current balance. Now, sometimes in life, you're unlucky. On the way here this morning, we have 2 independent bus services running roughly every 10 minutes. And I arrived at the other side of the road, crossing the bus stop, the other side, just in time to see one kind of bus immediately behind the other kind of bus, just receding into the distance. That's life. Bad luck is everywhere. But this turned out to be stupendous good luck. It took us quite a while to realise how good it was, because there are several advantages over the current balance. No coil size, shape, or current path measurements needed. Remember, it doesn't matter how the toroids thread one another, so a lot of that goes out. Virtual work principle. Now, to do the experiment, we're going to split it in 2 halves. First, we're going to weigh to determine the force with a current. And secondly, we're going to move the coil and measure the voltage. And splitting the measurement in 2 halves like that means that you're not talking about actual work. If you were, you would worry about friction in the bearings and air resistance and joule heating in the coil and all sorts of stuff like that. But it's virtual work. When you're weighing the coil, voltage doesn't come into it, coil isn't moving, and when you're moving the coil, there's in principle no force on it. So no actual work is done in bringing about that equation that I pointed out. And all you need, in principle, is one measurement of the velocity in order to satisfy that equation. It has to be vertical velocity, because by definition, force from weighing is vertical. Have to think, but that's not too difficult. But there's always a but, isn't there? There's always a but. We have to eliminate any velocity which might accidentally occur in the other 5 degrees of freedom. As well as moving up, the coil might move a bit sideways, it might rotate about 3 axes a little bit, and so on. All of those would produce a little extra voltage, wouldn't they? And that would cause an error. So it's quite vital that we align the coil to move vertically. And fortunately, since we're talking about vectors, we don't have to do this all that accurately. So it's not a big limitation, but there's a but. And now this again is a bit of stupendous good luck, I think it is anyway. All the things you've got to measure, like the voltage, the current, how you measure that voltage by the current is about 10 milliamps, so it will produce 1 volt when it flows through a 100 ohm resistor. I'm pointing at this, but this is no really use at all, is it? Press the right button. Yeah. These are all favourable magnitudes to measure to, well, these days, getting on for a part in a billion. And the velocity, well, if we have an interferometer to measure it, that's about typically 5,000 optical fringes a second. And 10 to the minus 5 of an optical fringe is doable. Have to be careful, but it's doable. Again, part in 10 to the 9th sort of stuff. G, that's depended as the years went by on the development of a commercial gravimeter, but now it claims accuracies of about 3 parts in a billion, so that's all right. And the kilogram. So we have to weigh to a few micrograms to get a few parts in 10 to the 9th. But the curious thing about balances, however big and heavy they are, and ours is massive, they seem to have a resolution of about a microgram, to be careful. That was true of the old current balance too, before convection currents got going. They're all of a suitable size. That's either elementary physics or stupendous good luck, depending which way you look at it. Here's our first Watt balance. It works in air. Now that was a limitation because the refractive index of air has to be measured by somebody and used to correct the distance, the velocity measurement, and also its buoyancy on the kilogram. And both of these are a few hundred parts per million. So to get the accuracy we wanted out of this, you had to measure the density and refractive index of the air very carefully. This was done by other people. We had to measure the barometric pressure and the temperature and all the things that go into a formula for it. But anyway, we did that. This is my great big permanent magnet. It's several tons. Its coal faces are, excuse the imperial units, about a foot in diameter, the working parts of them. The coil is a rectangular coil. It is not a precision coil. It does not need to be. It can be any old shape in principle. And the weighing is by substitution. The kilogram is on this side, and it's done in this manner, that you first of all lower a 500 gram mass, which doesn't have to be precise, on this side of the balance, and oppose it with a current pulling the coil down on this side. You observe that current. You then lower the actual kilogram you want to calibrate or use on this side and reverse the current, which produces an equal push up, and the balance is in equilibrium again. That makes the current change symmetrical, which is important for avoiding hysteresis problems in the magnet. So that's a useful thing to do. So that's how it works, and that's it. Now, a little divergent story. At the beginning, after this light on the road of Damascus phenomenon of inventing the formula, the Watt balance, the first thing I did was write a feasibility study in order to screw some money out of the NPL management to actually do it. And there was a conference at that time, and Bob Kukowski from NIST came to that conference, and he is my ultimate hero as a metrologist. He is fantastic and very, very bright. So I showed him this feasibility study and said, "Do you think this will work, Bob?" He took it away with him overnight, and he appeared the next morning and said, "Yeah, I think it might." And I knew then I was on to a surefire winner. Well, anyway, he went back to NIST, and the next thing I heard is that he'd rigged up an apparatus to sort of try it out, a crude apparatus. And the next thing after that I heard was that they had got a Watt balance of their own, which many of you will be familiar with. Like many things in the States, it is big, it is huge, it is 2 stories high from base to top, which keeps you in trim going up and down the stairs. It's in detail very different. The principle is exactly the same, but the coils are horizontal coils, and the force is provided by a superconducting solenoid, which is a right guzzler of liquid helium. And the balance is a wheel rather than a beam, and the ribbons of parallel fine wires come off the polished circumference of this wheel and act like balance. They did that to make the movement purely vertical, if the coil was, if the wheel was exact enough. And that worked. Now, we had our first success, I suppose, by 1990, which is a date we have heard before here. This, more or less straight away, after, remember the current balance, 20 parts per million, this more or less straight away was 100 times better. Bang, just like that. So, with some careful work to make sure that we had no wrong answers, problems, systematic errors, the usual sort of thing, takes years, unfortunately. By 1990, the CIPM was able to recommend that the electrical units now could be represented, very good choice of word, represented by fixed values of the Josephson constant, the voltage, and the quantum Hall von Klitzen constant for resistance. And that the absolute values, if you like, are not very different from these purely defined values, and the world was mostly content with the defined values and got on with life. So that was a great victory for us, and we had a little celebratory party at our house on the 1st of January 1990, when we stayed up to midnight in order to see the lights of the house go dim because the voltage unit changed by a part per million. And there was a leap second, and whether we could see that on the newly developed digital radio controlled clock, which Bryan Knight, some of you may know, had developed at NPL. Unfortunately, by midnight, we'd consumed the equivalent of too many alcoholic thermometers, and we missed both, but never mind. So anyway, that was a success. And, one extra enormous bit of good luck was right at the beginning. I was joined by Ian Robinson. And the good luck was that he possessed all the things I did not know. You've gathered by now that I'm computer pretty illiterate. And he was a whiz kid with it. And also with electronics, which we needed for low noise preamplifiers and that kind of thing. And he possessed, in short, all the skills that I did not possess to make the darn thing actually successful and work. So, it worked, it was successful, and then I can remember quite distinctly sitting in the lab with Ian after the 1st of January 1990 and saying, oh, that was all right, now what do we do? Well, we sat and thought for a little minute, but by that time we kind of realised that the V times I, I'll get this right in a minute, there we are, this V times I, which we can write as V generated by the coil times V prime, the voltage generated by the current flowing through the resistance R. The V's were linked to the Josephson constant. By that time we had linked our apparatus up to a Josephson array, and R could be measured by a cryogenic current comparator in terms of the von Klipping constant here. So that's how our measurements were derived. And now if you just kind of work that out, you find that the E's cancel, provided it's the same E in both cases, which is a little bit of a question, but the theoreticians assured us that they probably were. You have a direct link, you're left with H, some integers, some frequencies, and that's all. And you have to measure G and the velocity U, of course, but you have a direct link between M and H. And Mr. Einstein smiled in his grave because that's not connected to energy. Lovely. So if somebody would kindly tell us what Planck's constant was, numerically, we could tell them what their mass was. We could generate a newly defined kilogram. Okay, right, let's get on with it. Off out of chairs, roll up our sleeves. What do we need to do? Well, the old apparatus worked in air and achieved an accuracy of about 200 parts in a million. In a billion. We needed, the mass people, the IPM told us we really needed to make our target about 20 parts in a billion. So that's an increase of 10 times in accuracy. Well, that's all right. It's easy peasy. Let's just do it. So the first thing to do is to put the apparatus in a vacuum. So we did, and there's Ian Robinson and the usual.
Oh, you have 10 minutes.
I'm only on page 1. Okay, we'll get there. There's Ian Robinson, there's the thing in the vacuum. We've changed the geometry. Gone is the rectangular coil. It is now that's the wrong thing to do. That's the wrong thing to do. Can I have an extra minute and some help, please? How can we get out of this?
I have no idea.
Escape. Escape. So it's a good thing to press, isn't it?
Now I can go back to where I was. Yeah, the coil is now a toroidal coil in this lower vacuum chamber, and the magnet is essentially a loudspeaker magnet sitting on its back. You can imagine that. But it's the same old beam. It weighs 44 kilograms, if anybody wants to think of it as an efficient balance. But it works. And so we got on with it. And that's where all the trouble started. The years went by and various results were obtained, and the scatter is a bit horrendous. And observe the time scale. We are now talking a substantial period of 3 years. 3 years. It was obvious to us that we weren't aligning the apparatus well enough, and each time we realigned it, we got a different alignment, and so a different result. So Ian smothered the apparatus with autocollimators and mirrors to look at small rotations and non-contacting distance measuring gizmos to look at sideways movement, and went on. Now, I must just say that this looks terrible, and as if we are... Ian, by this time, I retired and left him in the lurch. He was a really rotten metrologist, but there are extenuating circumstances. One is that he had was given other things to do in this time. The other thing is that, of course, all sorts of little side investigations, like the hysteresis of the knife edges and little things like that, were done in this interval and dealt with and found problems solved and so on. All that was good. But also in this time, the NPL management decided that really ours looked like a rough old apparatus and we really should have a gold-plated one, and they set up a committee to design the next version of the Watt balance. And you know the old saying that a camel is a horse designed by a committee, and so Ian had to spend about 3 years of his time trying to ward off the more silly ideas generated by the committee. Anyway, there are a lot of excuses. But we finally arrived at a situation where the NPL management really sold itself and sold the whole apparatus, lock, stock and barrel, and indeed some of Ian's time, to Canada. Now, you will not, those who have not heard it before, will not believe this, but it's absolutely true. A date was set for the apparatus to be packed up in a container and shipped to Canada, an absolutely immovable date. 2 weeks before that date, Ian suddenly came to the conclusion that because of all these measurements with autocollimators made, that the alignment really was good enough. It must be something else. And he thought of the something else. And this is really stupid. We had decided in the beginning that we didn't need a pointer for the balance, as most ordinary balances do, because we were measuring the coil position with an interferometer, and in fact servoing the coil to a constant position.
5 minutes, Bryan.
And that, that dispensed, that was a monitor of the beam angle, and we didn't need a beam pointer. Wrong. Keep an eye on the counterweight on... Oh, done it again. How did we get out of this? Oh dear. I
I'll stand beside you.
Thank you, yes. I'll abandon this time. Anyway, keep an eye on the... don't get old, it's never worth it. This 500 gram counterweight here, it's shown in the lowered position. No, that's not what I want to do. That's right. What happened between those two? I have to... Oh dear, oh dear. I should... go forward one more, yeah. Yeah, it's raised. Okay, it's raised. Remember, this is servo to a constant position. The weight... How the hell does that work? Anyway, there's a change of force on the beam. I can't. these rods stretch, and the beam is at a different angle, and the balance was not adjusted to be acyclic. It had a restoring force due to its tilt. There's one error. Rather quickly, there's another one. Keep an eye on the kilogram mass this time. Oh, no. No. Thank you. Right, okay. Keep an eye on the kilogram mass. No.
Yeah.
Oh,
Did
no.
some.
I'll have to just pass on, but when that happens, the base of the balance tilts, and the central knife of the balance tilts. And so its point of contact changes, another error. The two errors Ian found in this 2 weeks left him do sort of cancel, but not completely. And he had no time to investigate their magnitude and make a correction. And anyway, it obviously changed over the years, that's why there's scatter. So, and we had designed in some weights right at the beginning to make the balance of periodic, and never used them. How stupid was that? Anyway, went to NRC with this knowledge imparted to them, and they made simple modifications, and the weighing went from what you see on the left immediately to what you see on the right. Much, much better. Much, much more consistent. Here's a set of weighing results. On the left is a scale in parts per billion, essentially, and quite clearly put an average through that to a few parts per billion, no problem. Velocity was not so good. The voltage generated divided by the velocity is plotted here. This is a succession of up and down movements, lots and lots of them going, taking place about every 10 seconds or so. And now the scale, the 1 sigma deviation of it is a substantial part of a part per million. Remember, we're aiming at a few parts in a billion. So that means you have to collect an awful number of points to average them. And clearly, an elephant-sized systematic error could be hiding in that long grass. Well, the Canadians now saw that, were quite properly very dissatisfied with it. Here it is again on the left, and spent a couple of years trying to track down where this additional noise was getting into the system. And after a couple of years, they got the idea that it had something to do with the interferometry, that the wavefront going through the interferometer was not as flat as it could or should be. So this again probably was my fault, that in a 45-degree mirror which reflected the beam up, I had put 4 screws in to hold it, maybe just for transit, but anyway that's the state they were in. So one of the screws needed to be loosened so that mirror could adopt its proper flat surface. So the smallest member of the Canadian team volunteered to crawl under the apparatus, and within a few minutes he loosened the screw, and the results you see on the right.
Bryan, you're in extra time.
Oh, thank you. Do I get paid for overtime? This means that it's a tenth the peak-to-peak noise, roughly. It means you need 1/100th only of the data points to get the same resolution. So they could investigate a lot of systematic errors. Let's pass on. The NSC results. It's important that you check you get the same result with several values of the mass because of possible non-linearity between the interaction of the current and the magnetic flux. They had that. The scale, you will note the graduations of 20 parts per billion apart. And I think you could agree that about 20 parts per billion could be ascribed to that, perhaps better. And this is not the only results they have, of course. And the result was a value of H, where the figure encircled in red is the important one, 19 parts per billion. And remember that the specification of the mass people to protect their kilogram was that there should be a result of 20 parts per billion or less. So that's good. The work on silicon atoms, which Richard in the last talk mentioned, came out with a result with about the same uncertainty. And what is incredible if you're a cynic like me, or wonderful if you are not, they agreed within that uncertainty. The NIST group struggled on with their monster over the years, and they obtained 35 parts per billion error, and within that error they agreed with this. So we would maintain, as of the present time, I don't want to show that just for a second. At the present time, all is well for redefining the kilogram. Now, here is something where our friend Murphy, he of the law of maximum cussedness, you can visualize rolling about the floor, howling with laughter, because the Canadians who had the apparatus found experimentally, and Ian, who did not have the apparatus, found theoretically, more or less independently, more or less at the same time, that alignment doesn't matter. You have to do the sums properly, remembering that it's a vector situation, but all these misalignment little bits of velocity and rotation and so on add up to modify the current balance equation, but it's still exact. So, the lesson from that is to beware of the obvious. And final slide, is Le Grand K in the museum? Well, no, it will still be used, but I have to justify the title of my talk, and the defining H will be for the purposes of the people who measure fundamental constants to ensure their consistency, or not if there's some new physics. Thank you.